So for the purpose of the video, this is a revision seminar for Maths 1M in 2014, and I'm going to be talking about matrices and linear equations. And here on the Maths Learning Centre's webpage, there's already some video worked examples for some specific bits of that course, and they were chosen from the Tute questions a few years ago. And you can have a look at them, and there's videos and handwritten examples of how to solve some problems to do with that. Okay. So there's a technical point I need to point out here. It's not technically the Maths Learning Centre's job to teach you the maths in your courses. It inevitably happens sometimes, but it's not technically my job to do that. What it is my job to do is to help everyone in the university succeed in learning the maths that people are trying to teach them. And so that means sometimes teaching it again, and a lot of the time giving you some advice about how to go about learning stuff. And so my hope is that by talking about this in a certain way, I'll be able to show you what I mean about how to learn things. So back here, this is from the learning skills seminar that we gave earlier in the year. It's about understanding concepts. And I just want to point out that there are four sort of major questions you should ask about any new object that you learn about in maths, and it will help you to understand it and to organise what you're thinking about it. So the first question you should ask, what is it? And also, what isn't it? And find yourself know the definition and list the things that are and things that aren't. You need to know the sorts of things that you can say about it, so sort of adjectives usually, that you can say about, whether it's this or that, or whether it's big or small, or things like that. You need to know the sorts of things that you can do to it, so addition, multiplication, that sort of stuff, and you need to know the sorts of things that you can do with it. So if you sort of follow that list, it will make it easier to organise what you're thinking about a mathematical object, so that you can understand it better. And in the other seminars that I've done in the past, I've done this list of things for complex numbers and polynomials and a few other stuff. Okay, so I'm going to try and run with that there, and what I'll do is I'll leave it up on computer B so that the people here in the room can see it. It won't go on the recording though, unless I specifically go over and have a look. So what I did when someone said, can you look at the matrices section of the course, is I went and I found the lecture notes for it. It's apparently lectures 11 to 15 are about matrices and linear equations. And that was really hard to find. They're not labelled by what's in them. It just says lecture 11 and lecture 12. It's really unhelpful. So if you listen to this, Sue, note for future. Label things. Make things much easier to find stuff in my uni. So I went and I printed it out, and it's not particularly helpful off of my uni because there's all these gaps. But it's not that bad. It does actually talk about what a matrix is, and it has on the next page some examples of things that are. Well, there would be if it was filled in. And it talks about some of the things we can do to them. And I'm just going to talk about these in slightly different order, probably, and get to the equation stuff fairly soon. So let's see. And you see, having talked now for about 7 minutes, enough time for people to come in so we can get to the good bit. So, matrices. Right, matrices are a mathematical object. And in order to understand a mathematical object, we should do this list. And you don't have to do it in the order it's presented. Just make sure you can fill out as much detail as you can about each of those headings as you can. So what is it? So what actually is a matrix? Well, according to your notes, it's a rectangular array of numbers. And that is all it is. Okay? So that's the definition That's the definition of what it is. At some point in your future, you may look at matrices that have complex numbers in them, which is lots of fun, but at the moment there'll be real numbers. So that's what it is, okay, and that's just what it says. But in order to understand anything, like human beings are not actually all that good at definitions. They're really good at looking at things that are and things that aren't and having a feel for how things are. So we need a list of things that are and things that are not. Okay, so your list of things that are, well, there's your classic vector matrix. It's a perfectly good matrix. That's an 8, by the way. It's got a rectangular array. It's 2 by 2, and it's got some numbers in it. And those numbers can be whatever we want. And they don't have to be whole numbers, though often they are, just to make the maths easier, so while you're still learning them, but they can be whatever numbers we like. Okay? Could even put a pi there or a root 7 if I wanted. Which, by the way, will come up in Maths 1A. So you should know how to deal with the ones with roots in them when you get there. Okay, so that's something that is. But there are some specific ones that are really useful to know about that they've given you a list of. So there's ones that like have names. Zero matrix has a name, so you could have any size you like, but as long as they're all zeros, that's what a zero matrix is. And there's one for every possible size of matrix, and that's what it's called. Okay. Now, while we're at it, we should know that we can talk about matrices as, listing what they are, but we can also give them names in the same way as any number can be given a name like x. You can give a number a name like x or a or b. Well, matrices can be given names too, and usually use capital letters for matrices. So the zero matrix is usually described by a capital O. So you use O for your zero matrix. Cool. There's also things that we call, for mathematicians, they're called vectors. Like that. Or column vectors. Something like that. And they're usually represented not with capital letters, but with, I'll just use 0 in algebra. So we'll be using something like, x with an underline or v with an underline in it in our algebra. Okay, for either column or row vectors. I should say that to a mathematician, it's always a column vector unless otherwise stated. So technically, we'll be using sort of x and v and u and that for these vectors, but these ones will usually have transposes on them because to most mathematicians assume that unless you say otherwise, a vector is supposed to be a column vector. So you put, I'll talk about transpose in a second, but that's how it's normally talked about. And then there's the identity matrix. Which has ones down the diagonal and zeros everywhere else. And it has to be square as well. Of course, you don't have to do all of these examples if you don't want, but that's what they're called. And we use the letter I in algebra. So when we're writing it down with sort of an algebraic thing, we use the letter I. And up here I should probably say use capital letters. Okay, so there's some examples of things that are matrices. It's really hard to come up with an example that's similar that's not a matrix, because like it wouldn't be a matrix unless I wanted to. I wouldn't write it down unless I wanted it to be a matrix. But that's what matrices are. They're just rectangular arrays. And on the face of it, you go, well, what's the point, right? You like just write rectangular arrays till cows come home. There's not really maths if you're just writing stuff down with numbers in it. But that's what they are. And the next point is what we can do to them that's the really good stuff. But let's just write down and see if we can come up with all of the stuff that you've been told so far that you can say about a matrix. Okay, so what can we say about a matrix? Well, we can say, so the list of things that we can say about a matrix, I'll just go back to the installed computer. We need to know what properties it can have, and how you tell if it can have them, what things belong to it, and how you find them, and what theorems tell you about it, and when they apply. And I might not be able to do all of these at once, so I'll come back and fill them in as we go. But they're the important things that we need to know. And what things belong to it sounds a bit vague at the moment, but it's sort of like with a function, it has a derivative. The derivative belongs to the function, so that's the sort of thing that we can do. So we need to know what things belong to the matrix and what can we say about them. So, well, the things that it belongs to it. So let's do some things that our matrix has. Things that belong to it. What it has is entries. Okay, that's the name of the numbers that are in the matrix. So these numbers that are in the matrix, they're called entries. And that's what they're called. And we should know how we should talk about entries. We talk about entries as being in a certain position in the matrix. So you can have the entry in row 5, position 6, or row 2, position 3, and you can talk about it like this. So it's good to say how we talk about it. So you can say that this is position 2, 3, because it's in row 2, position 3, okay? And what they normally use for those is the letters I and J. I for the row and J for the column, but it's not necessary to use those letters, and sometimes they'll switch it up and use a K instead, or use a J for the first one, but it's just good to know that they're normally called I and J. And you don't have to know about whether it has those, because all matrices have them. And there's a standard way of approaching writing them, is you traditionally use a small letter to represent the entries and the capital letter to represent the matrix. But you do, when you write it down, have to specify what small letter you're planning to use, because it's not always obvious when you, say with an identity matrix where small I is already reserved for what position you're in, you have to use a different letter. So you'll say a statement like, let A have entries A, I, J. That'll be a statement that you might say about a matrix. Okay, so that's something that it has. It has entries. What else have we got? Just looking through. Oh, it has a size. Matrices have sizes. Okay, we can talk about the size of a matrix, and we list how many rows it has and how many columns it has. So if it has R rows and C columns, isn't it? Then R by C. Okay, that's the size. Lovely. Okay, I tend to remember it as how high it is and how wide it is. I don't think of it in terms of rows and columns because I just draw a picture. So for example, a 3 by 7 will have 3 this way and 7 this way. And you'll fill in all the rest, right? That's how big a 3 by 7 matrix is. Okay. So there's some things that it has. I wonder what else the matrix has. I don't think you did determinants in Maths 1M, but in Maths 1A you'll find that a matrix has a determinant as well. And you'll find that, something else that belongs to a matrix is its reduced row echelon form. Yep. That's the other thing that belongs to a matrix. Okay, it's another matrix that belongs to your original one. I'm just talking about the grammar of it. You say that it has a reduced row echelon form. So, we'll just see later on that. But it's basically another matrix related to your original. I know this sounds a bit esoteric, but a matrix also has rows and columns. I know that sounds really odd, but it's really important to point out that a matrix is not just a rectangular array of numbers. Because the array of numbers is rectangular, you can split it up in all these different ways which are useful for different purposes. So if you saw a matrix like this, okay, it has rows, and those rows count as vectors in their own right. So you can actually at any moment perceive a matrix as made of its rows, and you can perceive it as made of its columns as well. And I know that sounds like it's a stupid thing to make such a fuss about, but it's really important to be able to see it as a collection of columns, because that makes span make more sense later. And in Maths 1A and in Maths 1B and in whatever other maths you do, it's really useful to be able to switch between seeing it as a collection of rows and seeing it as a collection of columns and seeing it as an object in its own right. You can even, if you want to, split it up into smaller matrices if you want to, like a big 4 by 4 matrix could have 4 2 by 2 matrices inside it, and that might help too, but we haven't really covered the usefulness of that in Maths 1M, and it probably doesn't come back. You probably will never see that unless you're doing the theory behind the linear regression in statistics. So we'll skip that. But it can be broken apart into its different pieces, and it's useful to do that because it helps you understand matrix multiplication and a whole lot of other stuff. So there's some stuff it has. And what we're getting into there is back here. What we're getting into here is knowing the ways to represent it. So that's this point here. Know how to represent your matrix and how to convert between them. We can represent our matrix as a collection of rows, and we can represent it as a collection of columns as well. Okay? In Maths 1A, you'll learn some quite fanciful ways of representing matrices by doing them as products of other matrices, and we'll get to that, but mostly at the moment in Maths 1M, we can represent it as a collection of rows and as a collection of columns. So going back to our document camera, if you gave each of these names, like A1, A2, and A3, then you could represent your original matrix, which we call A, as A1, A2, A3, and put these vertical bars to remind yourself that you're putting them in as columns. So that's a way of representing your matrix. And I know it sounds very basic, but it's useful to know that that's a way of representing it if you need to. Okay, right. Now we're into the really useful thing about matrices, which is what we can do with them. Okay, so mathematical objects, they may have begun life as something else. So for example, polynomials began life as functions, so they were just stuff that you can do to numbers, and then they take on a life of their own and become objects in their own right that we can do stuff to as an object of its own. And matrices start life that way, as a thing that you can do stuff to. So it's not just a matrix of rectangular array that you can break into pieces and say, oh look, here's a column. We can actually do things to them that are like the things that we do with numbers. And matrices are some of the first things that you meet that behave not like numbers. Okay, they behave a little bit like numbers and a little bit not like numbers in other ways. So what can we do? Alright, so we want to know what operations we can do, so things like plus, minus, times, what functions we can perform, and any information that we can find. We need to know those things, and we're going to try and make the connections to what it looks like if you represent things in a different way. Now this sort of thinking works extremely well for complex numbers, so have a look at that revision seminar if you're interested in knowing how I run through this with that. Okay, so what can we do? Well, we should do the ones that compare to ordinary numbers first. So the things that we can do are addition and subtraction. That's our first thing that we can do. And in order to add or subtract matrices, they have to be the same size, and I just add each entry separately. All the matching entries are added up separately. So add the matching entries, and it's only allowed if the same size. So before, with numbers, we were allowed to do addition whenever we wanted. That's what numbers were for. But addition and subtraction for matrices, we're only allowed to do it in certain circumstances. And it makes sense. If you have to add the matching entries, then the entries have to match in order to be able to add. So if there are some entries in one that don't match with the other, then you can't add them. So all the entries have to match with another entry in the other matrix in order to add them. And so you go, well, cool, they're the same size, so because every entry has a matching entry in the other one, and I can go, well, 3.5 would be 7 halves, 2 minus 1 is 1, 1 plus 6 is 7, 0 plus 6 is 6. And you just add all the matching entries in the same spot, and that's how you add matrices. And it doesn't matter how big they are, as long as they're the same size, you can add them. And subtract them, that's lovely. That's one of the things that matrices do. And in terms of, now this is an important thing, we need to know the rules for how matrices are allowed to add. So because we need to be able to do algebra, not just do it with the raw numbers, we have to say, well, if this is the matrix A and the matrix B, and they're just letters, we need to know what we're allowed to do with them. So one of the things we do need to know is that all the rules for addition and subtraction algebraically are the same as for numbers. Same laws for plus and minus as numbers. Okay, so for example, minus minus A is the same as plus A. Okay, they're the same things for addition. Okay, it's really important at any point when you learn how to do a procedure, especially in maths at university, that you learn how it looks when you do it in algebra. Okay, so what else can we do to our matrices? Well, we can multiply them as well, and here's where it gets fancy. Multiplication. That side. Okay, so multiplication of matrices is really quite complicated. And it seems rather it's amazing that someone came up with this really quite complex process for multiplying matrices. But it does make sense if you start with vectors. You've been doing matrix multiplication when you did dot products. Dot products are already matrix multiplication, so that's the start. Okay, so I'm going to relate that to that in a second, but the big idea for matrix multiplication is that each row of the first one is multiplied by each column of the second one, and that produces an entry in the answer. Okay, so those two together produce that number there, and then this row and that column produce the next one, and each row and each column combine together to produce an entry in the outcome. And that's a very vague picture that I've drawn you, I'm sorry, but I'll draw another one. So row I here and column J here combine to produce the entry here in row I and column J. Okay, that's the rules, and the way that they combine is that you multiply the matching entries in this with the matching entries in that, and you add them up. So it's literally a dot product of those two rows. So the simplest case is going something like that, and we go 1 times 2 is 2, 0 times 2 is 0, and 3 times minus 5 is minus 15, and then we have to add those answers together. You do not have to show all the working for this, because that's the basics, and you do all sorts of other stuff later, but if it helps, you can do that. So we'll have 1 times 2 is 2, 0 times 2 is 0, 3 times minus 5 is minus 15, and then we add all those answers together, and we get the number minus 13. Okay? And that's what would go in whatever position of the matrix I was interested in. Okay, this is literally a dot product. It's the same as a dot product for vectors. As you'll notice on the screen over there, are these actions similar or different to what you can do to other things? Well, they are. It's similar to what we can do to vectors because it's dot products. Okay? So you can actually represent dot products as matrix multiplications, which is really useful for, in particular, statistics, but for a whole lot of other things as well. I should probably just do one full example. Okay. I did neglect to mention something. The sizes have to match in just the right way. Okay, and it's not, for me, worth remembering a rule in my head for how the matching works, because I just look at my matrices and know if the things match properly, because just like with addition, every entry has to match with an entry in the second one, and if there aren't enough entries to match, you can't do it. Same deal with matrices. Every one of these has to match with one of the ones in the columns, because I have to go row times column, and it has to be a dot product. So the rows here have to have the same number as the row columns here, and they're both 3, and so it will actually work. But if it was only this long, without that bottom thing, there'd be 3 here and only 2 there, so I wouldn't be able to multiply. So 0 plus 0 plus 3, and that goes in that spot. So I've done row 1 and column 1. And I can keep using that row and go along this way if I want, or I can keep using those 2 rows and do it on the first column. Whichever works for you. I tend to stick with the same row and move my way along the columns and then move to the next row. So this row and that column I've done, this row and the next column, -1 and 6 is 5. This row and the next column, 2 and 6 is 8. And so now I've done the first row times the whole matrix produces this row here. And then the second row, 2, 1 plus 1 is 2, -2, -1 is -3, plus 2 is -1, and 4 plus 2 plus 2 is 8. And so this row times the whole matrix produces this row here. Okay, I could have, if I wanted to, do this, both of these rows times this first column and produced that 3, 2. So I could have just done the whole matrix times the first column and produced the answer 3, 2 as well. And this gets me to ways of representing stuff. It's really important to know that you can do it 1 column at a time in the answer, or in the second one, or 1 row at a time in the first one. Okay, so I could have said, if I wanted to, I could have called this A, and I could have called this V1, B1, B2, and B3. And in the answer, well, I could have done the whole of A times B1, and that would have produced the first column of the answer. And the whole of A times B2, and that would have produced the second column of the answer. And the whole of A times B3, and that would have produced the third column of the answer. So this is an algebra way of saying that I can do one column at a time if I want for the second matrix. Just so that you can see that that's a perfectly good possibility for doing the algebra, it's really good to be flexible in that way if you need to. Okay, so the dimensions match. In this way, you've got the number of columns of the first has to be equal to the number of rows of the second. Now, while we're at it, we should probably think about, there's a classic problem that says, you know, all of these are defined, how big are the matrices? I should probably do that now while we're thinking about how matrix multiplication works. So in this matching thing, so if you've got if A is 3 by 5 and B is 5 by 2, I know it's possible to multiply them because this matches with this. It'll be possible to do AB. It won't be possible to do BA because they don't match this way. Okay? So what I can actually do is I can go AB would be 3 by 5 times 5 by 2. And since those two match, it is actually possible. And the result will be 3 by 2. So these two outside ones will be the size of the result. And that's because you can run down the rows of A and every one of them will produce a row of the answer. As you saw, they can do the whole row, the row times whole matrix, and then the next row times the whole matrix. So you're going to get a row for every row in A, and you're going to get a column for every column in B as well. So that's how it works. And that means that you can do this classic problem which says, you know, A is 3 by 5, and B and C and D and E are some matrices for which that is defined. How big are all the matrices? Okay, that's one of the classic problems. Might put a squared there too. Now I haven't defined what squared means yet, but hopefully since you've seen the whole course we can do that. So this means that I have to be able to do all of these matrix multiplications in order. Okay, and B squared is BB. And so because AB is defined, B has to have a 5 in this spot. And because BB is defined, it has to be square. And we can keep out moving along there. So we could go, I could give them all names, right? So if the size is B, not that. You know, a number of rows of B, a number of columns of B for B, number of rows of C, a number of columns of C for C. And you can do that. It's always good to have names. And then we know that it has to be defined, right? So we've got 3 times 5 times BR times BC dot. So we can do that. Okay, and they all have to be defined. So because of this bit, BR has to be 5. Because of that bit. Because of this bit, BC has to be BR, because they have to match. But BR was 5. Because of this bit, BC has to be CR. But BC was 5. Because of this bit, now we don't know what CC is. So we're just going to have to leave that in reserve. And we can continue down that road. CC has to be DR. DC has to be ER. EC has to be ER. And so these are the last few, we don't know what they are, and that means I have made up a bad problem because it doesn't have a solution. And has 7 columns. Let's do that. Okay, so now we know that the final number of columns is actually going to be 3 by whatever this last thing is. So EC must be 7. Which means that ER is 7. Which means that DC is 7. And we still don't know what they are. They could be anything. Okay, that's okay. As long as they're the same. So it looks like we can have that A is 3 by 5, B is 5 by 5, C is 5 by CC, we don't know what that is, D is CC times 7, and E is 7 by 7, and it will work. They normally give it to you so that you can actually figure them all out. But you know, I made this up on the spot, so you've got to cut me some slack. Okay, but that's just a key, you know, a separate point, right? This is not about matrices, is that solving problems often means that if you can organise what you've got in the right way, then it'll be easy to solve. There are other ways to do this, but I find this the quickest way. Okay, now, multiplication, we need to know what rules it follows. So rules. Okay, so it's the same as all the rules for ordinary numbers except for the glaring issue of that AB is not necessarily the same as BA. Okay? So mostly AB is not the same as BA. Sometimes in rare circumstances it does come out right. But other than that, all the rules still work. Okay? Except you have to be really careful what side things are on. And that comes in really important with not solving equations because as long as you're careful, with the sides. So as an example, A times B plus C, you will be allowed to expand out the brackets, but because the A is on the left-hand side here, it has to be on the left-hand side of both of them. You're not allowed to just switch and change to whatever side you like as you go, which you could have done for numbers, right? For numbers it would be the same as BA plus AC, but it's not necessarily true for matrices. Okay, so yeah. Now what this literally means is we're supposed to figure out what the plus is first and then multiply by A, but we can, if we want to, do these multiplications separately and then add. Okay, so just be really careful, so not. Okay, it's not that, because we have to be careful that it's on the correct side. And that makes it really important when you solve matrix equations later, that you make sure that you're imagining having the entirety of what's there and multiplying on one side or on the other. You can't stick matrices in the middle. Now there's a couple of other rules. When you do multiplication, there is a particular number that if you multiply it by stuff, nothing happens, and that's the number 1. Well, matrices have one of those as well. Okay, for any A. Depending on the size of the matrix A, those two I's might actually be different to each other. So as an example, our matrix there, if I want to multiply by an identity on the right-hand side, it has to be this big, because this number of that has to match that size. But if you want to multiply one on the other side, it'll only be this big, because this has to match that. So in order to specify the difference between those two identities, we often call this one I3 and this one I2. Just so we can tell that they're different sizes, but do be aware that AI equals A and IA equals A, there might actually be different identity matrices. Yeah. Alright. Well, there's two more things that we can, while we're at it. The other stuff we can do to numbers would be to do powers, right? Just making sure I haven't lost the order of my pages. We can do powers. Oh, I suppose while I'm at it before I do powers, A times O is O. But I should point out that this O and this O might be different sizes. Yep. Actually, worth noting in terms of the sizes, that A times column vector will be new column vector. They'll both be column vectors, possibly different number of coordinates depending on how big A is. Okay, and that's just to do with the sizes. You've got like n times m and m times 1, and this will be something times 1. And it goes for rows as well. You know, I'll call it by a different number. Okay, so these will both be row vectors. It's just good to know that that happens. Yeah. And also note that you can't put a column matrix on the left, a column vector on the left-hand side of a matrix, because it won't be the right size to match. Okay, so you'll never see XA where X is a column vector, because it doesn't. The sizes won't match, so you won't be able to multiply them at all. That's a hint, therefore, that anytime you see AX, the X has to be a column vector, because it can't go on that side unless it is. Okay. Now, I was in the middle of doing something. Oh yes, powers. Okay, so powers are defined the way powers were defined when you first saw them in probably primary school, possibly high school, depending on which school you went to. Powers are defined by just doing repeated multiplication. Okay? So powers is just repeated multiplication, which means that, you know, a squared is a times a, and a cubed is a times a times a, and so on. There you go, which means you can only put a whole number up here in the power because you're only allowed to actually repeatedly multiply a whole number of times. You can't do 1.5 a's multiplied together because there's no such thing as a square root of a matrix. And even if there is a matrix that does have a square root, it could have infinitely many square roots. So there's just no, square roots don't exist for matrices. So you can't have half powers. So only whole numbers. Except for the thing that a to the 0 is defined to be I. And a to the 1 is defined to be a. And it will only work for square matrices as well. Because the number of, to do a times a, the number of rows of a, the number of columns of a has to match with the number of rows of a, so they have to have the same number of rows and columns, and therefore it has to be square. Of course, this is true for any matrices. Okay, and the same rules for powers work. When you multiply two a's together, the powers will add. So the same rules, you know, a cubed times a to the 5 will be a to the 8, and a squared to the 7 will be a to the 14. So the same rules apply as numbers, except there's no such thing as roots. Okay. All right, so that's all the things that numbers do, right? We've done addition and subtraction. We've done multiplication. We haven't done division. I'm not going to cover that. Division is done by matrix inverses, and that's in Maths 1A. But that's what's done. So division is really tricky for matrices, so we're not even going to cover it. And we've done powers. There's no such thing as roots. So what else is there left? Well, there's the things that matrices do that numbers don't. So what have we got? Multiplication by a scalar. You can get a single number and multiply the entire matrix by that number all in one go. Okay? So you can get, e.g., 3 times the matrix 1, 0, 3, 5 would be 3, 0, 9, 15. We just multiply everything in the matrix by the scalar. Numbers don't do that. Well, of course, for numbers it's just ordinary multiplication, but that's something that matrices do that numbers don't. And in terms of the algebra, we need to know how that interacts with all the other things that we're used to. So with algebra, this would be like Ka that we call it. So we need to know how does that interact with multiplication and with addition and that sort of thing. Well, K of A plus B, I can expand brackets. K of AB, well, I could put the K with the A, or if I wanted to, I could put the K with the B. So that allows me to do algebra when I do matrix equations. With powers, I'll just do both of them to a power. So that's great. Okay, and that's exactly how ordinary numbers can be manipulated in algebra, and so it follows the same rules pretty much. Okay, cool. This one's better in reverse. If you have K times A times B, that means you can bring the K out the front. And it's worth pointing out that this is from a pure mathematician's perspective, that minus 1 times A is the same as minus A. Now that sounds stupid, but minus A is defined to be whatever it is you add to A to get the zero matrix, and minus 1 times A is defined differently, and so to a mathematician it's really important to point out that they're actually the same thing. Yeah. Oh, and 0 times A will be the zero matrix, right? I don't know. Note that this is a number and this one's a matrix. Yay. Okay, so just the point I want to make is that when you get to any new thing that you didn't know how to deal with before, that's a brand new thing that numbers didn't do, you need to know how it interacts with all the other stuff that you can do. Well, what else can we do? We can do transpose. So matrices are rectangular arrays. We can switch them around and do them as, and convert all the rows to columns or all the columns to rows. That's what transpose is. Convert rows to columns or columns to rows, if you like. That's what the transpose does. And we write it as a power, which means that when we look at it in algebra, we always do it before addition. Okay? So written as A transpose, and you do before plus and minus, and also before times. Okay? So because it's written as a power, and the ordinary order of operations says that you should do powers before addition, subtraction and multiplication, so we always do transpose in an expression like that before we do addition and multiplication. So that means that AB, i.e. AB transpose, means A of B transpose, not AB then transpose. Oh yeah, okay. Right, so that's transpose. Now, you may have been taught it, possibly at school, as flipping your matrix along its main diagonal, but I find that really confusing when my matrix isn't square, and so I find it easier just to run down the rows or columns and flip them. So, e.g. if A is like that, then A transpose. So I've got two choices. I could use the rows or the columns. I choose whichever is longer, and I know that the first row of A becomes the first column of A transpose. Sorry, column, crap. The first column of A becomes the first row of A transpose, and the second column of A becomes the second column of A transpose. And I do it one column at a time. It stops me from getting it wrong. Whereas if I try to imagine literally flipping it like that, ooh. Good thing at banging it made it come back again. Oh, there was a whole year when revision seminars were all in blue, because yeah, Fletchy was one of the first ones to get document cameras, so poor old thing's getting a bit crusty. So okay, so I find it easier to do it one row or column at a time, and it's worth pointing out that if you have a single row, when you transpose it, it will be a single column. And I should also point out that while I traditionally use square brackets for matrices, sometimes I will use round brackets and nobody cares. Okay, so whatever works for you. You're supposed to be consistent. It's like in English, you're supposed to, you're supposed to be consistent with the way you use your punctuation and grammar. You're supposed to be consistent. If you like to use square brackets, you're supposed to use them all the time. But mathematicians are fairly sloppy with brackets, so just do whatever you feel. Okay. And worth pointing out that when a mathematician wants to specify a row or specify a column in text, they'll often specify it like this with a little t there to remind you that it's really supposed to be a column. Okay, so it's just one of those things. But they don't like, they waste all this white space if you put it in as a column, so we'll put it in as a row and then it will fit neatly in your assignment and it won't blow out to 5 pages when you're doing vectors. So that's the only reason, it's just for typing purposes. And you've got to imagine when people had to do maths on a typewriter, whoa, it's insane, so you want to keep it nice and compact. They used to have people who would type all the maths assignments and they'd have to handwrite the integral sign when they finished them. Yes, now we have a fancy program called LaTeX, spelled L-A-T-E-X. So have fun searching that on the internet. Yeah, I really think that that Knuth, who invented it, could have thought more carefully, but anyway. Maybe he deliberately did that because he thought it was funny. Okay, so that's transpose, and we need to know how transpose interacts with all of the other things we know how to do, so addition and subtraction and multiplication and powers and scale multiplication. Okay, and just because it's simple flipping, it doesn't really affect anything, right? So if you add them and then transpose, well, you could just as easily have transposed them and then added them and it wouldn't have mattered. For scalar multiplication, if you multiply it and then transpose, well, you could have transposed it and then multiplied and that would have been fine. Powers, a squared transpose, well, you could have transposed it and then powered it and that would have been fine as well. Okay, and that works for any power. And that's one of the reasons they write it as a power, because it interacts with powers in a useful way. The only problem is that it does stuff up your multiplication a little bit. So because all your rows have become columns and all your columns have become rows, and because matrix multiplication is highly dependent on which one has the rows and which one has the columns, you need to switch the order when you transpose. With multiplication. And that works in as many as you like, so you know A, B, C, C transpose, B transpose, A transpose. Okay, so you just literally reverse the order. Really important to remember, because it might not be even possible to multiply them the other way around, so you've got to keep the order. And it's to do with matrix multiplication being really dependent on which one you're considering is the rows and which one you're considering is the columns. Okay. Right. So let's see where we've come. Just need to do a little recap. So we had matrices and they were rectangular arrays and we were allowed to put any numbers we want. There were some special ones that had names of their own and then we were able to talk about the size. We were able to split them into rows and columns because that sometimes helps. And then we were able to do addition, we were able to do subtraction, we were able to do multiplication, but that had some, special, sub clauses that say, "Ooh, not allowed to do it here." There was powers, there was scalar multiplication, there was transpose. So they're the things that we know how to do. So just as a summary so far, so we can do addition and subtraction, we can do multiplication, we can do powers, we can do transpose, we can do scalar multiplication. That's what we can do. That's my extreme summary, right? Which is what you're supposed to do when you're studying. Yep?
With the transpose, AB transpose has to be B and A has to be reversed for everything?
Yep.
A, B, C, D, E would be E, D.
Yep, exactly. So ABC would be CBA. If I had A, B, C, D, E, it would be E, D, C, B, A. You'd have to put it in the opposite order. I have a couple of people laughing because I've recited the alphabet backwards to them before. So should read Cat and Hat Comes Back. It's got alphabet backwards in it. So I'm really good at that book with my kids. Okay, so yes, you have to reverse them, literally reverse the order. Okay, that's what we can do to matrices, but there is one more thing we can do which doesn't feel like any of the other stuff. We can do row operations. Okay, why you would want to do row, I should do it properly. Why you would want to do row operations is to do with what you can do with the row operations, like what you can do with it, as opposed to what you can do to it. So I might get to that in a minute. But what you can do to matrices is row operations. Technically you can do column operations, but nobody cares because you just transpose it and do row operations. So we're just going to do row operations. And there are really good reasons why column operations are a bad idea to do with, well, we'll get there. So you can do row operations. And technically you can do any row operation you want. It's just that it might have unpleasant ramifications if you do the wrong kind. So there are 3 basic elementary row operations you're allowed to do. Okay, so we can do multiply just a single row by a scalar. Not the whole matrix, just one row. And they have particular notation for writing them down. Different lecturers have different preferences, and whatever works for you, as long as you're consistent, will be fine. I tend to write this as my new, like, row 1 is like 5, row 1, something like that. Possibly without the word new. That's a very computer science way of writing it, without the word new. That's a very computer science way of writing it, because row operations only really came into the fore when computers became small enough to be useful. Other people will write it like this, and still others will write it like this. Whatever works for you, okay? I find this one difficult to understand, because I actually imagine it as pulling out the row you've got, doing something to it, and then putting it back. And so I imagine this as 5 blocks of row 1 is put into the position that row 1 is in. That's how I think about it with the arrows, but whatever, just be consistent. The second one you're allowed to do is switch any rows. Which extends to basically rearranging the rows however you want, right? So, but technically it's switch 2 rows. I tend to write it like the new row 1 and row 2 is the old row 2 and row 1, which is cumbersome. Other people write row 1 and then a double arrow row 2 like that. That's the shortest way of writing it, but being a mathematician I have to be consistent, so if I'm going to use the other one I have to use this one. And then the other one is you can add on a multiple of one row onto another one, as long as you keep it in the position that the one you're adding onto is. And I know that really doesn't make any sense when you listen to it. So add multiple of one row to another. Okay, the key with this one is to notice that the row, that position you're in, if I'm in position row 1, I bring another row in, okay? So you can do this one with the arrows as well. Or the arrow going the other way. You're bringing a multiple of another row into this row, so the row you're in has to stay the same as it is, except for the other row coming on top of it. Okay, so you're not allowed to, so non-elementary row operations, you know, 5 of row 1 minus 3 of row 2 goes into row 1. That's not an elementary row operation. It's a perfectly good row operation, and it will not break most things. You know, most of the time that'll be perfectly fine, and there won't be any issues with that. You're not allowed to do that one. You have to split that into 5 of row 1 and then row 1 minus 3 of row 2. Okay, you have to do that as 2 row operations. And it's just for theoretical reasons, and also for teaching a computer to do these reasons, it's easier to only have 3 possible options. Okay, so that's not elementary, and also non-elementary is this one, like that. I know the row 1 is all by itself, but it's been minused, and that counts as multiplying it by minus 1. Okay, so just pointing that out now. So it's good to know the things that are and the things that aren't. These are the things that are, and these are not. And you're definitely not allowed to do row 1 minus row 1. That's just completely pointless. So definitely not. Okay. Yeah. Technically, the scale is not allowed to be 0. You're not allowed to multiply row by 0. You could, but it would be just a waste of time. So don't. And it would severely change the properties of your matrix. Okay, so you're allowed to do row operations. And the whole point of doing row operations is actually to use your matrix in a particular context, but it is something that you're allowed to do to matrices. And you can follow them on one after the other, and you can do them in whatever order you want, but if you do them in a different order, the results will be different. But if you do but with a particular purpose in mind, you will get to a certain place, and that is the reduced row echelon form. So the place we're headed for is the place where we have as many zeros as we can in the matrix, and as many numbers as we can that aren't zero are 1. That's the whole purpose of it. Okay, we want to make our matrix look as much like an identity matrix as we possibly can. That's the whole point of row operations. So the aim here is to look like an identity matrix. Now, if your matrix isn't square, it's not going to look particularly much like the identity matrix, but you'll do the best you can. And your aim is actually to make is to look at the columns of the identity and make your matrix have those columns in the same order the identity has them in. Okay? So you want columns of the identity. That's our aim. We'll do a proper example of that when we get to what the whole point of the row operations is for. Okay, that's our aim. Look like the identity and make one column of the identity at a time. I find it easier to make one column at a time. Some people like to make the zeros below and then the zeros above. Whatever works for you. Alright. So in terms of raw objects of matrices, that's as much as in Math 1M. Okay, there's other stuff you can do to them. You can find inverses and you can find eigenvalues. They're awesome fun, and you can diagonalize it, and you can change the basis, and you can make row spaces and column spaces, and this is all stuff that's in Maths 1A and Maths 1B. So you're going to do lots of more stuff on matrices, and so we'll just add to this list as we go of stuff we can do to matrices. And determinants too. Stuff we can do to matrices, there's quite a long list because they're bigger than numbers, so we can do more, but this is what you've got in Maths 1M. Right. We're now up to the last bit. I reckon I'm probably not going to get to the Euler's method, but we'll do what we can. What can you do with it? Okay? So I'm not going to talk about the other objects you can make from it, because that's in Maths 1B, but I am going to talk about the problems that you can solve with a matrix. Okay? And the problems that you can solve with a matrix are problems involving linear equations. Okay, so what can we do with it? We can solve linear equations. I must say there was one thing that I missed right at the beginning, which is when you do have a new object, you need to have a way of telling whether they're equal. And matrices are equal if all their entries match. But that's fairly obvious. But most things that aren't numbers have a specific rule for telling if they're the same. Okay, solve linear equations. So that's what we can do with matrices. And the reason it works is because we can pitch linear equations as matrix equations. Okay, let's make that tail on that y less extreme. So this is a linear equation. Okay, well, 3 linear equations actually. So before we move on, it seems to me that the connection between this and what you did in the vectors part of the course seems to be fairly shakily made. Well, this is the thing. One linear equation in 3D is a plane. We spent ages, at least I did in the Maths Learning Centre, talking all about Cartesian equations of planes. Well, that there is the Cartesian equation of a plane. Each of those linear equations represents a single plane in 3D space. Okay? So that there represents three planes in 3D space. Each equation represents its own plane. Okay? And the The point of having a Cartesian equation was to tell you where the points are on the plane. So if I wanted to know whether the point 1, 7 was on the first plane, I'd sub 1 in for x and 7 in for y, and if it came out to 5, which it doesn't, then it would be on the plane, and since it doesn't, it's not on the plane. And so if I had a point and I wanted to know if it was in all three planes, I would sub it into all three equations. If it came out to 5 for the first one and 3 for the second one and 7 for the third one, then it would be in all three. Okay? So if I want to find all the points that are in all three planes, I have to find all the x, y's and z's that satisfy all three equations at the same time, so simultaneously. So when you look at this, each of them separately represents a plane, but together they represent whatever the points are that are in all three planes simultaneously. That's the whole point of doing linear equations, is that's where it started anyway, is trying to find the thing that satisfies all three and to find the intersection of planes, or whatever the objects are. If they're in 7-dimensional space, they're not called planes, but that's, it works anyway. So we can write this as a matrix, because what we can do is, first we can say, well, what if this was a column vector? Like that. Okay? And then we were just told that the first coordinate of this column vector is 5, but it's also 3x plus 2y. And the second coordinate is 3, but it's also x minus y plus 2z. No, just plus z. And the third coordinate is 7, but it's also a half of x plus 3z. So I can write this as a vector. So now, in order for those three equations to be simultaneously true, this vector, whatever it is, has to be equal to this vector. You have to pick the right x's and y's so that this comes out to 5, 3, 7. Now that was only really a superficial change, but the next stage is to be really clever about the fact that we can now write it with a matrix, because just that bit there, the 3x plus 2y, that could be a dot product, with an x, y, z and a 3, 2, 0. Three times x plus 2 times y plus 0 times z. And this row, well, that would be a dot product between 1 and minus 1 and 1. And this one would be a half, 0, 3. That's the magic, where the matrix comes in. There is an alternative way of splitting that up as well, which is where span comes from. So at this stage we're splitting it up for a matrix, and now if we wanted to know whether the point 105 was in all three planes at once, we could stick 105 here, do the matrix multiplication. If it came out to 537, yes it is, and if it doesn't, then no it's not. Okay, so I can tell simultaneously if a point is in all three of those planes by doing a matrix calculation rather than three separate algebra calculations, which is something that makes it ever so slightly simpler. Okay, now here's the really cool magic. I know that if whatever, these two equations are certainly both true, and I know that I can add to this side whatever I want to add to that side. So I could have, 3x plus 2y plus 6 is 11 if I wanted, or I could have 3x plus 2y plus x is 5 plus x. I could do any number of things, but the other thing I can do is, well, knowing that this is the same as that, I could add 3 to both sides, and I could add 3 here and get 8, and this is another way of writing 3, so I could add that here. So since I can add the same thing to both sides, I can add the equations together, and I can multiply the equations by stuff, and I can put the equations in whatever order I want, and those operations on matrices, equations correspond to operations on matrices. So those row operations, what they will do is they will turn my equations into a better set of equations that's easier to read and easier to calculate with. And I also know that if I did stuff on here, it would affect the 537. So if I want to do operations on this stuff, I need to do the same operations on the 5. So what I'm going to do is I'm going to join these two bits together into a single matrix. Now, an augmented matrix isn't a real thing, right? Mathematically, it's just a big matrix, which you may have gotten if you've ever tried to do it in MATLAB or Wolfram Alpha. It doesn't. The computer and mathematics itself, the God that is maths, does not understand that there is a line here. It's only an augmented matrix in our minds because we are remembering that this represents the coefficients of the equation and this represents the answers. Now you are allowed to go direct from the equations to the augmented matrix. Okay, you don't have to go through the intermediate steps. That's just the theory as to how it works. So you're allowed to go direct to there, but if it makes you feel better, you can do that too. And I should point out to you that you still need to know that this bit of working is there, because every so often they'll ask you, can you write it as AX equals B? Where this is A, this is X, and this is B. Okay? Okay, every so often they'll ask you to do that, and so you need to know which bit of which corresponds. This is the matrix A, this is the vector X, this is the vector B. Okay? Worth pointing out. So what you do with your augmented matrix is you do row operations, elementary row operations, to get it as close to the identity as you can manage, and then once you're at that stage, it'll tell you all about what happens, all about the intersection of those three planes. Now, I must say there was a really good example that Sue did in lecture somewhere, 13, 14. It's actually labelled, it has worked example for row operations, okay? And she goes through several examples where you do the row operations and you get to a certain stage and then you say, ta-da, this is the answer. And it may or may not, it probably has in it a way of choosing which row operation to do. Because it's all well and good to say you could do row operations, but you could just start doing row operations willy-nilly and end up turning it into a matrix where all of the numbers are in the 700s and it's not useful at all. So you need to have a strategy for choosing what to do next, and that's what I'd like to tell you now. So my strategy for choosing what to do next is to A, avoid fractions, and B, well, focus on each column at a time. Okay, so the aim here is to make my matrix as close to the identity as possible. I will focus on this column and I'll say I need to make that into the first column of the identity. This is what I'm aiming for. Okay, so I need a 1 in the first position, and you usually make the 1 first. But if you can make the zeros first, then that's fine as well. So I need a 1 in the first position. I could totally get that by swapping the first two rows. Okay, and I compare what I've got to my aim. My aim was to get the first column of the identity matrix there, and I currently have the 1 in the correct spot, so that's good. I've got that bit there. And now I need the zeros, and this is the only time you're allowed to do two row operations at the same time. You're allowed to make those two zeros simultaneously if you want. So I can use, and this is what that third row operation is for. I'm going to get my new row 2. It's going to be my old row 2 minus 3 lots of row 1. And I'm going to get my new row 3, it's going to be my old row 3 minus a half of row 1. And if I do both of those, it'll clear these zeros and I'll have gotten my first column. And then I can move on to the second column. And I can make the 1 and then the zeros, and then I can move on to the third column. Have a look at the worked examples on the Maths Learning Centre's webpage, which will be near this seminar once it's finished, because they will... I talk through my methodology for doing that in every example, so you'll get a handle on how I think about it. And if that helps you, lovely. If it distracts you and you've got a method of your own, just use your method if it works. Okay? It's worth pointing out that some people, and my students taught me this, do a little calculation on the side to tell them what they've done. So you can go like calculation for this row operation here. I've got my old row 2, which was 3205, minus 3 lots of row 1. I'm supposed to add them together. So this is my row 2, this is my minus 3 row 1, and then if I add them together I get 0, 5, minus 3, minus 4, and that helps them to focus without having to do it all in their head. And I actually really like that particular approach because it prevents mistakes, and that's what you want in an exam, okay, you know, preventing mistakes. And so now I'm going to, what this is telling me is I'm going to replace my old row 2 with this. And I could also do my row 3 minus a half of row 1. And that is 0, and that's a half, and 3 minus a half would be 2 1/2, which would be 5 halves, and 7 minus 3 halves would be 5 1/2, which would be 11 halves. And then I can put that all back in my matrix. So my row 1 didn't change. My row 2 became this. And my row 3 became this. Okay, so now what I've done is I've managed to create my entire first column of my identity, and I'll move on to the second column. I need this to be at the column of the identity, so I need a 1 in this position just here, and a 0 in both other positions. So I've got several choices to make, and I'll make the 1 first. I could divide everything by 5, but then I'd have fractions in fifths and halves simultaneously. But if I multiply this one by 2, that would be awesome, because then I'll be able to get a 1 without too much extra work. So that's the approach that I would generally take to get the one where I want. It'd give me 2 extra row operations, but I would avoid fractions, and I know that fractions cause me to have more errors, and so therefore I avoid them. Of course, if you've got a calculator that can do reduced row echelon form, you can ask it to do it for you, unless they explicitly tell you to show all your row operations, right? So, yeah. And they really commonly do a matrix that has like a pronumeral in it, like a C or something, and so you're forced to do it by hand. But they are fairly nice. They won't expect you to do too many row operations all at once because they know you've only got 2 hours. So they usually only expect you to do 1 or 2 or 3 and you won't have to do too many. So I would continue down that road. So my next choice, my next thing that tells me what to do is to choose how am I going to make a 1 in that spot. And then once I've made the 1, then I can clear the zeros. If you talk to some other students, you'll get some other really nice strategies, and I recommend doing that. Some people will multiply the matrix up, and so they can avoid fractions completely and make them both 4 and then subtract to get the 0. That works quite well in some situations. But the reason we teach you the elementary ones is that a computer, 5 and 27.832 are the same to a computer, technically. They don't worry about fractions, so if you just tell it to always divide by whatever's there and then do all these things, it will get to there eventually. Okay, the key is what do I do at the end, right? I get to the end of my matrix, my reduced row echelon form, and then I have to interpret what I see. I have to get the solutions, and I have to get the solutions, and I have to interpret what it means if those things were planes to begin with. And lots of people find that last step quite difficult, and so I just thought I'd just have a chat about that. What do I do now? Well, what I do now is I look for free variables, well, pivots first, then free variables, and then I create my solutions. Okay? So, these ones, right, that'll come down here, they're called pivots. That's what they're called. And you find the columns that have pivots in them, and they are called basic variables for no good reason. The columns that don't have any pivots, the variables that they came from, are called free variables. And then what you'll do is you'll get your free variables and you'll give them names other than the names they already have. Technically, you're allowed to call them x and y if they were already x and y, but it's traditionally you call them s and t. And then you solve for the basic variables. And that's what it says right here in your notes. Okay? Okay, now you may be familiar with this, but I want to point something out because I want to connect it to something else. So while, I've said here that we should be making connections, and all of these advices that I give say you should make connections because the sensation of understanding happens when connections are made. You don't feel you understand, and you don't actually understand until you connect it to something else. Okay, that's the way your brain works. Your brain cells have to be connected for you to feel like you understand. So, I'm going to connect this to the vectors stuff. So, I'm just going to take a 3 by 3 one. So used to writing R for real numbers. Suppose that's my reduced row echelon form. Okay, so what I'm going to do is I'm going to look at this, and that's an identity matrix column, right? And so therefore it's a pivot, and that's my second column as well. Right. That's my second column of the identity. It's a pivot too, and this one doesn't have a column of the identity in it. If there was a 1 there, I would have kept doing row operations and finished it off. Okay, so first thing to notice in this one is that 0 plus 0 plus 0. Okay, now that's really dodgy what I just said. This is not 0 plus 0 plus 0, okay? Because this here is not 0 plus 1 plus minus 2. Coincidentally, that actually is minus 1, okay? But note that 1 plus 3 is not 2, okay? So that doesn't mean that my equations are wrong, because this does not mean 1 plus 0 plus 3 equals 2. It means 1x and 0y and 3z is 2. So there are some other numbers in this formula that we haven't put in this picture. The x, this is one lot of x and no lots of y and 3 lots of z. Whatever x and y, z are, x, y and z are, they are numbers of their own. And when I combine them with this 1, 0, z, 3, then it produces 2. So no x's and no y's and no z's can only be 0. That's the only thing it can possibly be, no matter what x and y and z are, and that can't possibly be 6. So there's no solutions. That's the first thing you should look for before you do anything else. You should look to see if there are any solutions at all. So you can look and see, is there a 0, 0, 0 anything other than 0? And it doesn't have to be a 1, it can be anything. And then, if there is, then there's no solutions and you can stop. Okay? So, and it doesn't have to be in the last row, it can be in any row. If you get all row of zeros and then something not 0 in the answers column, no solutions. But from ours, it's from the final row. That would mean, now, let's just think what this means. The solutions are points in 3D space. You're used to thinking of vectors as arrows, but as I've said to many of you before, vectors are points most of the time to a mathematician. So this x, y, z represents the coordinates of a point. And if that point was able to satisfy all 3 equations simultaneously, then my 3 planes would meet, would have that point in their intersection. And since there are no solutions, there are no points in the intersection. So there are no points common to all 3 planes. Now, not to say that it's not possible for the first 2 planes to meet. Okay, it might be that the first 2 planes do meet, and the third one sort of is parallel to the second one or something. Or it might be that any pair of them meet and the three lines that they make are parallel, and so there's no points in common to all three. So if you see no solutions, the safest thing to say is there are no points in all three planes, or however many planes there are. Okay. And if you're in 2D, they wouldn't be planes, they would be lines. So you've got to keep track of where you are. We're in 3D because there's an X, Y, and a Z. Okay. That's the first thing to look for. I'm so used to writing real numbers that I just write a blackboard bold R no matter what. Okay, suppose it's this time. And now there is a row of zeros, but I need to point out to you that rows of zeros, unless you're in this first situation, rows of zeros are completely irrelevant. Okay? Do not focus on the rows of zeros. It's not going to help you. Unless your original matrix is square, the rows of zeros are just not helpful. So don't focus on them. You're supposed to be focusing on the pivots. The rows of zeros are all about telling whether there's a solution at all. Okay, so we're going to look at this and go, oh, row of zeros. Just check, oh, that's zero as well? Cool, I can ignore that row now. That row is now dead to me. I'm going to move on to the other rows. So, my other rows, that's what's going to tell me what the solution is and how many solutions there are. Okay? Okay, so I do get solutions. So there are solutions. That's the first thing to notice. And it's worth checking that every time. Look for your rows of zeros. See if the answers column is also zero. If it's not, there's no solutions. But if it is, you can declare that there actually are solutions. Okay? And then you can look for your pivots. So I have a pivot here, the pivot column there, and a pivot column there. My third column doesn't have a pivot, doesn't have one of those ones that would belong to an identity, and so therefore it's free. My third variable is free because it doesn't have a pivot. And so that's when I start. Traditionally you call it T, no real good reason, but that's just how you do it. I think one of the reasons you call it T is because a lot of these situations it's actually an object moving in space because of time, but that's just really after the fact. It helps me remember. Let Z be T. So I'm saying, look, the whole point is that this equation doesn't tell me anything useful about Z. You know, it tells me nothing useful about Z at all. Okay, so that means that Z can be whatever I want. So it can be T, and T could be 5 and minus 7 and 200 billion and pi and 0 and any number I want. So I call it T. And then I figure out what the x and y are in terms of T. So this first equation says that x plus 3z is 2. And so therefore I'm going to get that x is 2 minus 3z, but z is T. And y is minus 1 plus 2z. You can do that in multiple steps if that works for you. I've just done this for so long that I'm used to doing it all in one go. So if you do want me to do it in multiple steps later on when you feel not so embarrassed to put your hand up and say what you're doing there, David, I'm happy with that because there's no such thing as embarrassment at the Maths Learning Centre. In a lecture theatre you can feel very embarrassed, so I'm not going to put you on the spot. So that's how I do it. I actually usually look at, I have this and then minus off those numbers. That's how I do it all as one vector in my head. And then your aim now, and that's cool, I've got everything now. Notice this is very much like the parametric equation of something. In fact, this is the parametric version of a line. And the reason I know it's a line is because there's only one variable. It's a t. If there was both a t and an s, it would be a plane. So the next step is to go, well, this is how I was taught anyway. So x is 2 minus 3t, y is minus 1 plus 2t, and z is t. And this is the stage way back when we were doing vectors where we learned how to create the vector equation from the parametric equation. So it's the same story. Okay? That's not a z there, that's a 2, by the way. Okay? So what we're going to do is we're going to separate this into two vectors. A vector that contains all of the plane numbers. I've got 2 as a plane number, minus 1 as a plane number. This one doesn't have any numbers not attached to t, so that'll be a 0. And then I've got the vector with the t's. So I've got minus 3 lots of t, 2 lots of t, and 1 lot of t. And that's how it's done. And look, that is the vector version of a line. Therefore, if I take all of the points that are in all three planes, what I make is a line, because that's what that is. Okay. So before, back when we were doing vectors, if we needed to find the line where two planes met, we'd have to do some really fancy work, you know, with vector equations and like normal vectors and stuff. Now we can just use matrices, and there's the answer. Okay? Right. And it is possible that you will just get a solution because you'll get 1, 1, 1. Okay? The key is to focus on the right things at the right times. The 0 rows only tell you whether there's solutions, so once you've decided whether there's solutions at all, write that down, there are no solutions or there are solutions, and move on and ignore all the rows of zeros. After that, then you can start trying to find what the solutions are. And I should point out to you that if you've got one of those ones where there's an unknown number, and it says, you know, what does k have to be in order for there to be no solutions or whatever? Well, you go the no solutions, then you go the unique solutions, and then everything else has to be infinitely many because there's only 3 options. So, yes. If you want to know more about that, feel free to talk to anyone who's done Math Track. Or me, obviously, or anyone in the Maths Learning Centre. Okay. Right. Well, that's pretty much everything, except for span, and so I should just mention that. Do you know the other thing we can do with matrices? Is we can make spans. Okay. Technically we don't need a matrix to make a span, we just need vectors. But matrices, as I've mentioned before, have handy collections of vectors. So they're really good for making spans. So I need to tell you what span is. Span is a really big idea in maths, like in linear algebra, and you'll spend weeks doing span in Maths 1A. Of course, no one will understand it then either, which is why we have a Maths Learning Centre. If we can get it down pat now, you'll be so set up for Maths 1A. So, all right. So, this spans isn't really about matrices, it's about vectors. Now, you've thought of vectors as points, and you've been able to use those points to make lines and planes. You've thought of vectors as arrows, and you've been able to put them head to tail and add them. So if we're thinking about vectors as objects in their own right, there are 2 things you can do to a vector. You can add them. Add them. Subtracting doesn't really count because you're just multiplying one of them by minus 1. And there's the key, you can multiply them by numbers. Okay, so you've got these vectors, and to a mathematician, a vector is just something that you can, in a consistent way, add and multiply by a number. Okay, so to a mathematician, the set of all possible functions, well, they're vectors too, because I can add them and I can multiply them by whatever. And matrices are vectors to mathematicians as well. And so, you know, mathematicians are pretty clever. They can make anything look like what they want. Not nearly as clever as, say, astronomers, who can really make anything look like whatever they want. There's a really famous example of taking data on Venus, on the thickness of the crust. And I saw this interview and there were 5 scientists from the same data, but all said different things on how thick the crust of Venus was. So there you go. But that's science for you. That's why we have a community of scientists. They can all talk to each other and come up with some sort of consensus, hopefully. And sometimes they don't, and therefore we don't know anything at all. Maths, however, is so much easier, right? Because things are just true in maths. So what we can make is spans. So the whole point is to do addition and scalar multiplication. And if you do addition and scalar multiplication simultaneously, it's called making a linear combination. Okay? So linear combination of v and u and w, they're vectors. See, I put underlines on them, you can tell they're vectors. Would be something like whatever that comes out to, that answer is a linear combination. So just as an example, I could do, u plus b, that'd be a perfectly good one. 5u plus 6, sorry, not b, v. 6v minus 215w. I could also just have like 7w. That would be a perfectly good linear combination of all three because it's technically 0u plus 0v plus w. And the other classic linear combination is the 0 vector because it's 0u plus 0v plus 0w. So note 0 with an underline under it is the vector that has all zeros in it. So at matrices we'd write a capital O, but 0 vector, we've got that. I say that because one of the maths lecturers, Jono, who teaches Statistical Practice 1, did not realise until third year that that's what the 0 with an underline meant. Okay, so I say it just in case. Okay, so, and he's a very smart person, right? He's become one of the lecturers. So that's what 0 with an underline meant. It means 0 as a vector, it's a vector all whose coordinates are 0. And all of these are perfectly valid linear combinations, okay? I don't have to use all three of them, and I can use none of them if I want and make the 0 vector. A span is what you get if you do all the linear combinations and you collect them all together into a set. That is the span of those three vectors. I'm just going to check the notation in Maths 1M because it might be different to Maths 1. Nope, okay. Okay, I say combos there, linear combinations. So u, v and w, I get all the possible linear combinations of those three and I colour them all in. I get this picture in space and I go, well, which vectors points here are linear combinations? It's that one, it's that one, it's that one. I colour them all in and the object I get at the end is the span of all the linear combinations. All of those three vectors. So grammatically, in terms of grammar in maths, the statement of v is in the span of 102 and 311 is the same as the statement v is a linear combination of 102 and 311. They are the same statement. They mean the same thing. Worthy of note, because they'll sometimes say, is V a linear combination of those things? Or they'll sometimes say, is V in the span? They mean the same thing. And why is this connected to matrices? Well, here we go. What's what happens when you multiply a matrix by a vector in the right sort of way? Okay, I'm going to do this. AX. So my A could be 3 columns, right? Or 4 or 5 or however many it has, but I'll do 3. And I'll call them A1, Well, V1A, because they're vectors. As I said, you can think of your matrix as being made of 3 vectors. And X, well, that would be X, Y, Z. Now, here we go. How can I do matrix multiplication? I could go the whole matrix times the first column and then the whole matrix times the second column. That would work. I could do this row times that whole thing, this row times that whole thing, this row times that whole thing. There is one more way of thinking matrix multiplication, and that is just treating it as if it was an ordinary dot product. This times this, plus this times this, plus this times this. So, having a matrix and multiplying it by a column means that what you're doing is you're specifying a linear combination of the columns to do. Let me give you some examples to really ram this home. Choose a nice long matrix. Now, I could, if I wanted to, go this times this, this times this, this times this. But I could use what I know about how matrix multiplication works and say, well, this ought to be 1 of the first column, none of the second column, none of the third column, and none of the fourth column. So it would be 3, 0, 1. This is telling me I should do 1 of the first column and minus 1 of the second column and none of the other 2. So it should be 3 minus 2, 0. Because I'll go that minus that, that minus that, that minus that. Thinking about it that way, well, it does help you to reason about matrix multiplication and do it a little quicker. But the whole point of it is to realise that what I've done here is I've just used this to tell me what combination of columns to do. So multiplying a matrix by a column is the same as making a linear combination, which means that when you span some vectors, if you whack them as columns in a matrix and multiply by all the possible vectors, it will make the span. Which means that if I want to know if a particular vector is a span, I want to know, so asking V is in the span of 3, 0, 1, 0, 2, 1, 1, 2, minus 1, and 5, 6, 3. That question is the same as saying that A, this is the matrix A, times something equals V. And there is a V that works, an X that works. That is why matrices are related to spans, because any span can be written as AX equals B. And we know how to deal with AX equals B. It's augmented matrices and row operations. Okay? So both of those things, they're related. If you're thinking of your matrix as rows, your rows will represent equations and probably planes. If you're thinking of your matrix as columns, well, there'll be points and it'll be a span. So it's really good to know that they're both there, and so you use the same procedure to answer both questions. So now, rows, yay, no, rows. Okay, so that's how you solve a span question. You chuck the vectors as columns in a matrix, stick the vector you're interested in as your answers, do row operations, and if there are any solutions at all, then it is in the span. So in this case, we're not actually looking for solving for the free variables. All we're looking for is for that row of zeros. Is there a solution at all? Which means technically we don't have to go all the way to the reduced row echelon form. If halfway you can tell that if you finished it, it would give you a unique solution, then you can stop and say there is a solution. Okay, you don't have to go all the way. Okay, I just back here. Back here, at this stage here, I could have split this up in a different way, the same way that I split up the other things, and I just wanted to point that out just to make my point even more strongly. Okay. Right. So that's where I was when I was doing my linear equations thing, and I turned it into a matrix at this stage. I can turn this into a vector thing at this stage. I can have a vector with all the x's, a vector with all the y's, a vector with all the, sorry, there's two y's in the top row, and a vector with all the z's. And then I can bring the x out, bring the y out, and bring the z out. And now it's a span question. It's a question of, is this in the span of those three vectors? So the same question, it could be, do those linear equations have a solution? But you could also ask, is this vector in the span of those three? And the procedure is the same, and depending on what you were trying to achieve, you answer it in the way that you need to answer. Just pointing out one more time that spanning is to do with the columns of the vector, of the matrix. You'll notice that these were the original columns of your matrix. And solving equations is to do with the rows, but they both are solved with row operations. Right, well, I have actually booked potentially all day, so feel free to ask me any questions. You may be quite tired, I am, but I'm happy to stay. So do you want to ask anything else before I turn off the recording? Because what you ask might benefit somebody. Yes?
Could you explain finding the general solution?
Oh yes, I knew there was that, I forgot that. Yes. Also something they do in Maths 1A because no one understands it from Maths 1M. So don't feel bad. The point of that is to say, actually, it's not the most straightforward thing. So, okay. All right, so this is the homogeneous general solution thing. I will not be offended if you leave. So. Okay, now this is sort of this technical side issue, okay? And the thing that makes this hard is it requires you to simultaneously think of your matrix equation as equations and vectors, and if you think about it in both ways, it will make more sense. So, okay, so the classic example, I'm just going to see if I can find the one in the notes. So the idea is, you want to solve an equation, you know, like this one that we had here, but with matrices. And it may be that you're actually interested in multiple equations like that, but you've just got different answers. So you may have, you know, the 3x plus 2y equals something, and the x minus y plus z equals something, and the half of x plus 3z equals something. and you may want to solve the same set of equations for different somethings. Okay, so that's the context that we're in. We have the same this part, but we want to change this part and try it for a whole lot of different spots. A whole lot of different things here. Oh, 5, 3, 7, okay. Well, what if it was 0, 1, 1? What would the answer be then? What if it was 20 minus 6, 4? What would the answer be then? That's our perspective here. Okay. So if you're thinking that, then you're thinking, well, if I'm trying to know what all the different answers are, if I put different numbers in here, the simplest set of numbers to put in this spot would be 0, 0, 0. That's going to be the easiest one that go in that spot. That's going to be the easiest one to solve because it will definitely have a solution. Because I can pick x and y and z to all be 0 and there will be a solution. So I won't have to worry about that whole no solution situation. I'll only have to worry about the infinitely many versus unique. So that's the idea behind it. So what we have is I wish I had one that was already finished, but that's okay. I'm going to make up a new one. Give me a second. Thinking music while I think about it. Okay, we're back. So, here's my equation. X plus 5y plus 2z, yep, is 3. Y plus z is... Right. Don't press so hard, David. Y plus z is 1. X plus 3y plus 7z is 6. So there's some equations, right? And they would represent 3 planes. And I would want to know where they are. Okay. Right, so I can turn this into this matrix equation. And I'm thinking, well, what if I change these numbers here? Okay, so if I change those numbers in terms of spans, I could be asking, you know, oh, well, this vector is part of the span, but what about this vector? And what about this vector? And what about this vector? If I did it in terms of planes, I could say, well, sure, I've got a plane of this slope. If I change this number here, that will just move that plane up and down. So I have the x plus 5y plus 2z will be wherever it is. If it's equal to 3, it'll be down here. If it's equal to 7, it'll be up here. And I'm saying if I'm going to shift my planes around so that they all pass through some other point, what is that point? That's my question. So I'm going to do the one where I know it's guaranteed to go through the origin, which will be what happens when they're all 0. So this is called a non-homogeneous equation because these are not 0. So I'm going to make the homogeneous one. So my homogeneous version is technically this. Okay? So my homogeneous version has all zeros. And I'm going to solve that instead. Because firstly, it's easier. And secondly, the theory makes it work. Okay. Oh, I should have really... Didn't think that through, did I? Oh well, it's okay. It's going to have a unique solution, but we'll run with that in a second. I'll do another one in a minute. So that's the homogeneous one, and so I'm going to see, look, I'm going to arrange my planes, or whatever they are, to go through the origin. I'm going to see if there's any other solutions as well. Obviously the origin is one of them, but I want to know if there's a line or something like that. Okay, and so I'm going to have to do my matrix thing. And the nice thing is that when I do my row operations, this bit isn't going to change. It'll always be 0 because that's how row operations work. didn't change that one. That become a 0, that become minus 3. 0, 0, 1. And then row 1 is row 1 plus 3 of row 2. And row 2 is row 2 minus row 3, sorry. And ta-da! Unique solution. Okay? Lovely. That was totally easy. I didn't plan that one particular one in advance. I just knew there would be a solution for the other one. So I get a unique solution. Okay, so but the point is, I don't want to say it's unique. I want to say what the solution actually is. So the solution is that x is 0, y is 0, and z is 0. Okay, that's the only solution I get. Now, here's the fancy bit. Let's just think what would happen if we had a solution for the other one. What if we had some numbers that to go here that did come out to 316? Okay. So, if there was another one that came out to 316, I'm just going to put this on a separate piece. So we have ax equals my b, which was 316. What if there was another one? You know, what if I had two solutions to this? Then if I subtract these equations, so I'll subtract the equations. So what if two solutions? Yeah. Well, look, whatever this is, let's call that x3, is a solution to the one where it comes out to 0. Okay? So that means that from any two of the other one, I can make one that comes out to 0. So I should be able to work backwards and say, well, from one of the ones that comes out to b and one of the ones that comes out to 0, I should be able to make a new one that comes out to b. So that's, you know, a sketch of the proof that if I find all the solutions where it comes out to 0, I'll actually be able to find all the solutions where it comes out to b, as long as I've got a place to start. Okay? So, backwards, you know, start with x1 with ax equals b, add on all solutions h, and you'll get all the possible things for that, and that's all the solutions. Okay, so it's just a bit of theory and it's just a little bit of matrix algebra. In terms of what's going on spatially, if you get a matrix times vector equals answer, what you'll make is like a line or a plane or something like that. Okay, so you do all the solutions and you get a plane or you get a line or you get whatever you get. If you want to make it come out to a different answer, you just shift it over a bit. Okay, so it might be that you will have a plane and it's here through the origin. If you want to come out to 7, if you want to come out to a particular point, we'll shift it over here and it'll be another one. But that whole plane in one spot, sorry for those listening, you're not going to be able to see my hand waving. So this whole plane here is that plane plus a vector. Okay, because there is a vector that describes how to get from here to here. And the same vector describes how to get from here to here and from here to here. So in the same way that if I move my hand, the vector that tells me how to get from my thumb to my other thumb is the same as the one that tells me how to get from this finger to that finger. So it doesn't matter which point I pick, I will be able to get a matching point over there by going the same vector. So if I add the same vector to all of these ones, it will give me all of these ones. That's the visual thing behind it. So what this means is, all I need to do is all I need to do is find all the solutions for when it's 0, and then that's great. I need a starting point for the one where it's not 0, and I just tack them all on and it gives me all the rest of the solutions. So you just need this starting point, okay? So what I need to make the solution, and that's called the general solution. So what I need to make the solutions to solve Ax equals b, I could first solve Ax equals 0, and you'll get, some solutions. Find a starting point, which is called a particular solution. And then all the other solutions will be start here at this particular solution and go by all of them, and you'll get all the rest of the solutions. So add them together and you'll get a general solution. Okay, that's the procedure. So going back to where I was going. So I was here, and this is all the possible solutions to Ax equals 0. I only get one, but it's the only one I've got. That's telling me that if I've got 3 planes oriented by those slopes, if I shift them all to the origin, I'm only going to get the origin. There's going to be 1 point. So no matter how I shift those 3 planes, if I've got 2 of them here and I shift that one up, it'll still only meet in 1 point. And I shift this one over, it'll still only meet in 1 point. If I shift it over here, it'll still only meet in 1 point. No matter where I shift those planes to, as long as I maintain this part, you'll only ever get a unique solution. So all I need to do is find that starting point. I need to find 1 point that is on all 3 planes. And I just need to find that by a different method, because I've done row operations. So one way of being sure is I know which... What? I know which row operations got from 0, 0, 0 to the answer, so I could chuck in my 3, 1, 6 into here and just do these row operations just on the 3, 1, 6, and it would do the trick. And that would be my surefire way of figuring it out. Okay? But there is another way. Okay, so this here is the general solution to the homogeneous case. Okay? The next stage is to go back to the original. Okay. So now we find a particular solution. Okay, so my general solution to homogeneous case was done using row operations. My particular solution to the original case is done using some other method. And that method is thinking of this as combinations of the columns. I want to look at these columns and attempt to think of a combination of them that comes out to 3, 1, 6. So, all right. The first thing to try is to see if the vector you have is already one of those columns. No. All right, well, it was worth a try. The next thing would be to start seeing if it's a multiple of one of the columns. Well, it can't be a multiple of the first one because it hasn't got 0 in the middle. It can't be a multiple of the other 2 because if it had 1 in the middle, it would have to be equal. Okay, so now I'm going to try starting to add the columns together. So the first 2 columns would be 6, 1, 2. The first and the last would be 3, 1. Aha! It's the first column and the last column. And so I've got 1 of the first column, none of the second column, and 1 of the third column. That comes out to 3, 1, 6. So I you have to, it's trial and error, you try to create a combination of the columns that produces the answer. So that's a particular solution, because 1 of the first column and 1 of the last column produces the correct answer. So column number 1 times 1, column number 2 times 0, column number 3 times 1. And so my general solution, so therefore x equals the particular solution I just got and the general solution I got before is the general solution now. And it turns out that there's only a unique solution because I only get one answer. The general solution doesn't change from the particular one. Okay? Let me do another one. Going to skip to the matrix part if you don't mind. Have to think carefully, so yeah. Okay, right. It's really hard to do that. So here is one, another one. I'll do the same trick. So the homogeneous one, my homogeneous case. Oop, homogeneous case has 0, 0, 0 there. Oh, minus 16, yay, okay. 12 threes would be 36. Or have I stuffed this royally? Just give me a minute. Nope, it should work. I may resort to asking a computer to help me with this. Twelve times 3 is 36, yeah, okay. These two should be multiples of each other and they're not, so I'm really worried. If only you could change the question in the exam, right? Sorry? Yeah, I've just drawn my original matrix wrong, so just give me a second. But the rows are combinations of each other. Ah, this should be an 11. All right. Disaster averted. Yeah, okay, cool. Right. Sorry? Sorry. Disaster averted, the original equation now has an 11 in this spot. So I take off 11 of row 1 and I get this. And you'll see that this row is twice that row. So I can do row 3 is row 3 minus 2 of row 2. So I'm not going to get a pivot in this third column, so there's not going to be a unique solution. But there will be solutions, so therefore it's infinitely many. And technically I should be dividing this by and then row 1 is row 1 minus 3 of row 2. And I get my favourite fraction, minus 3/8. Well, plus 3/8 is my favourite fraction, but that's close enough. Okay, so now I get, these are pivots, and so I get a free variable in this column. So Z is free, so let Z be t, and then x will be 0 plus 3/8 of t, and y will be 0 plus 1/8 of t minus 1/8 of t. And so my x, y, z. So my x is 3/8 of t, not 38. 3/8 of t. My y is minus 1/8 of t. My z is t. And I can bring the t out. And I get that for my solution. So you notice this is a line because it's got only one free variable, and it goes through the origin because it's 0 plus t of that. So the thing is that those three planes meet in a line through the origin, but the original three planes, the ones that didn't have 0, 0, 0, they would meet in a line as well. It would just be somewhere else, and I just need to figure out where it is. Okay. So I go back to find my particular solution. So that homogeneous case is really the same as what you've always been doing, but I go back to find my particular solution. So I go back to the original matrix, and I attempt to think of something that goes in this spot. And this is the bit that's not usually taught explicitly. So I know that doing this will do a combination of those columns, and so I attempt to find a combination of those columns that comes out to this. So first I check to see if this column is already there. Nope. Next I see if it's a multiple of one of these columns. So if it were a 6, that would have to be a 30. No. It's 2 of that one. 3 times 2 is 6, minus 1 times 2 is minus 2, and 1 times 2 is 2. It's 2 of the middle column. So it's none of the first column, 2 of the second column, and none of the third column. That's my particular solution. And so therefore, I should get my other solution and add it onto this one. So therefore x equals my particular solution plus my general solution. So particular solution plus the homogeneous solution gives me the general solution. That's how it's done. And so I should be able to, now of course in practice that's actually not how it's done, because if you had a computer you might as well just get it to do the raw operations for you anyway. And most real problems don't have whole numbers, like, just face it. However, the theory of this particular solution, general solution thing, comes back when you do differential equations in Maths 1B, so you use it in a different context. So that's why they teach it to you now. And also just because it's mildly interesting. So, the key is that stage where you go, what combination of these columns is it to get the outcome? And one reason why that works is that A, it's the theory, and B, that's how your lecturer came up with the exam question. Not that I know what the exam questions are, but if there was an exam question that had that, that's how they would have come up with it, because they've been trained to think this way. So knowing how your lecturer thinks is useful. All right. Anything else?
So how does that help you when you want to, this is a stupid question, but how does this help you when you want to vary, you don't want to do the solution all the time, different situation?
It's mainly because in some problems you actually know one of the answers because it's the one you've got. So there are lots of situations, and it usually comes up in differential equations, where it's the physics that tells you what numbers go in those formulas, okay, in those equations. And then there's the situation which tells you what goes in the answer. And so there are times when you can know one particular answer because it's the one that works for you when you just built it, you're a model today, and you want to know what all the other answers are, so you solve it for the 0, and then you can add on the one you've got. But that's really vague because I'm not a physicist, so I don't use it. I actually only know the real context here, which is in functions, which is a whole different story. So when you're doing it in differential equations, you have particular rules for what things are likely to work as particular solutions. And so you try them and find one that works, and there's particular methods for that. So it does cut down on work in that in differential equations, but not so much in matrices. But yes, it would mean that really from a lecturer's perspective, it means that they can come up with examples till the cows come home by doing combinations of vectors to put this answer here. But yeah, in practice you just stick it as a column and do that. I would say that this may not be, but to answer a different question to what you asked, was if you did have the same this part here and multiple of these, what you would actually do in practice, solve and so on, right? So if you had the original problem, this is an ABC, and you had multiple things to go in that spot and you wanted to solve them all at the same time, you could solve the homogeneous one and attempt to think of a solution that comes out to each of these answers. That's how it would cut down on the work. If you had to do it by hand, you would go, well, I know that all of these would be some particular answer plus this. So the one where this goes in that spot, it would be something plus this. This one would be something plus this. This one would give me something plus this. So it would cut down on my work eventually if I could just happen to think of something that goes in these spots. But in practice what you would actually do is you would row reduce this. You would just augment your matrix multiple times and you would row reduce that. And then that's right, so you'd end up with your, what did it come out to? And you'd get stuff here, like that, if I did my row operations. And you could look at this and read off the solution to that one. You could look at this and read off the solution to that one, and look at this and read off the solution to that one. And so that's how in practice you would do it if you had multiple ones to do. You wouldn't really do the homogeneous whatever. The real purpose of teaching you that is so that later on, in other contexts, it looks familiar. So, yeah. That's what you would actually do if you had multiple ones to do. Yeah, and actually this answer here is going to be that. Because it'll be, 0 plus 3/8, 2 minus an eighth of t. So it'll match with whatever the solution was supposed to be. But if you happen to think of another random particular solution that was different, it would still work okay. Yeah. But in practice, that's what you'd actually do. And you could have any number of them here and their operations would work fine on all of them simultaneously. Right.
It's sort of like a more type thing. You do it, try and see what happens.
That's right. And I guess it's good to know that there are these sorts of methods if they are whole numbers, because then you can have a quick look. Yeah. Sometimes the stuff we teach you isn't relevant anymore because it was used before there were computers. And sometimes it's not relevant directly to you because it's just of theoretical interest to a mathematician. And sometimes it really is useful. And sometimes it's only useful because it's similar to something else that is useful. And so having learned this, even though it's not the same, you'll be better prepared to learn something else. So, yeah. And sometimes it's a good practice generally to say, well, what would happen if I had to do it this way? And what would happen if the question was this? And so, yeah. That's what I would do if I had multiple of them to do at once. I would do this. But if my exam question said, part A, solve it for 0, and then said, what are the solutions for these? Then I would attempt to do it by particular solution, because that would be the quickest way. Because I would already have done the operations, and because I didn't read ahead, I wouldn't have done with these. So in terms of efficiency, when I haven't done the best plan to begin with, sometimes it's quicker to do this. It's one of those things where you say, well, what if I'd gotten to this stage and now I had to do this? Is there an efficient way of not having to reinvent the wheel? And that's the idea behind it. If I'd already done the one where it's 0, I could attempt to figure out these without having to do the operations again. So, yeah. So there's several answers, one of which may be the one you're looking for. All right. That will probably do for now. I should probably eat something.
23.